Thank you for the invitation. So what I want to discuss today is the notion of bounded reminder set, which is a notion which has to do with discrepancy. So bounded reminder sets are sets which behave very well in terms of discrepancy. And then I will develop a symbolic and a dynamical view on these bounded reminder sets. So just to put the notation, we start, as usual in discrepancy theory, with the most classical example of well-distributed sequences, Kronecker sequences. So I'm here in a D-dimensional framework. I take some parameter alpha with entries which are Q-linearly dependent. One alpha D are Q-linearly independent. I consider a Kronecker sequence with values in 0, 1 to the D or in the D-dimensional torus. And to consider such a sequence, it's often useful to have a dynamical viewpoint. We are just considering a translation on the torus, and we consider the orbit under the action of this torus of the starting point 0. So that's the setting, the arithmetical and dynamical system setting. On one hand, a sequence, a Kronecker sequence, which behaves well. We have this rational independence, which gives some denseness result, equidistributions results. And on the other hand, we have a dynamical system and translation. So the usual viewpoint is a global viewpoint on such sequences, which consists in looking at the discrepancy globally. That is to say, taking the supremum on some let's say decent sets, so let's say boxes, for instance, so we take the supremum on boxes of the difference between the number of times you visit some box minus what you expect. So I renormalize multiplying by n here. So what we expect is that for the first n terms, we spend n times measure of the box time. So we just compare the time spent somewhere minus what is expected. So that's the global property of discrepancy. So it's here defined in terms of box. And we have a lot of nice results like 0-1 laws, like this one from Kitchen, the case D equal one-dimensional case, or put by Beck in the D-dimensional case, that says classically that the discrepancy is between something which is in log n to the d and some term log n and log n 1 plus epsilon. When I say between, it's that we have this 0-1 law, so given by some convergence or divergence of some function. So here I take log n to the 1 plus epsilon. And then we know that for almost every parameter alpha, the discrepancy is smaller than this, and there are infinitely many n's for which the discrepancy is larger than this lower bound. Okay, so that's the classical behavior when you take the supremum on all boxes for a Kronecker sequence. That is to say, this quantity has no reason to be bounded at all. It's in log n to the dimension in terms of growth. But what is interesting is to have a local viewpoint on this instead of having this global viewpoint. And locally, one can look at sets, not necessarily boxes, sets, let's say measurable for which this local discrepancy, when you don't take the supremum on all boxes, but when you fix one given set X, so you might wonder whether such sets exist, sets for which the time spent in some given subset X minus the expected value, which is still big N times the measure of this set. So one might wonder whether such a quantity can be bounded. So do there exist such sets for which the equidistribution locally is so good that you do not reach this log n to the d bound, but you have a bounded difference. So uniform bounded difference in terms of n, number of points that you consider, that tells you that you visibly set roughly as n linearly in the size of this set up to some constant. So that's the notion of bounded reminder set. It's local. So what do we know about them? So it's well known since the 60s from Kesten that the intervals which behave that well in terms of discrepancy are related to the parameter of the translation. So they belong to alpha z mod 1. And then there's been a series of papers on this notion, and it started also with the work of Schmidt on irregularities of distributions. But then the higher dimensional version of this result occurred much later, so in the 2015 and then 2017 for some very nice geometric proof of the original result by Grepstadt and Leff. And this statement, which plays the rule of Kesten, says that if you take a parallelotop, if you want to get a bounded reminder set, so the condition, the Kesten condition, which was your related mod 1 to alpha z, becomes that the vertices of this parallelotop have to belong to mod 1 to something directed by the vector alpha. So alpha is a d-dimensional vector, so I'm taking d vectors, and they have to be related to this vector alpha, to this translation parameter. In this way, these vertices belong to z alpha plus zd. So it's a sufficient condition for saying that it's a bounded reminder set. So the proof from Grepstadt and Leff is based on functional analysis, co-boundary equations, and it's, let's say, Fourier analysis analytical. And then the proof by Heinz, Kelly, and Koivusalo is really geometric and uses ideas usual in this framework is to look at things not only in the d-dimensional space, but in the d+1 dimensional space, and have a geometric viewpoint on this.
Sorry, Valerie, just one question. Are these by Christopher? Are these conditions also necessary?
As necessary, so they will not be necessary because you can have sets which are not parallelotops. As necessary conditions, you can have conditions saying that the measure of a bounded reminder set have to belong to the additive group generated by the coordinates of alpha. And then, so that's sufficient conditions. But in this paper by Grepstadt and Leff, you have very nice characterizations of bounded reminder sets, at least in the dimension 2. You have further conditions like some kind of properties of symmetry in the parallelotop. Thank you for the question. So my point in this lecture will be to escape the parallelotop world. So we will see other examples of bounded reminder sets which are not parallelotops. And maybe Christophe's question was about, is it a necessary condition when you are a parallelotop? So if you're not a parallelotop, okay, you have other possibilities. And when you have a parallelotop, then it's necessary. I have to think more. No, it's not a necessary condition. Yeah. Thank you. Now, the viewpoint I want to have on this is to focus on these sets which behave very well and ask further requirements. So the further requirement that I consider here might seem at first view a bit unnatural. The question is, what about points that belong to some bounded reminder set and that fall again under the action of the dynamics, under the translation, again the same set? Well, that requires that the set X is not too small for being able to be in it, and after one application of the translation, being again the set. So we can ask these kind of questions. But we can do something even better, and which is maybe motivated by viewpoint, which comes from symbolic dynamics, dynamical system. It's, is it possible to have a partition of the space into bounded reminder sets and to have conditions telling you that if you look at the situation, then you apply your translation, you still get bounded reminder sets. So this is the idea I want to convey now. But to do that, I would like to first give a convenient illustration of a translation on the torus, just for us to have some geometrical viewpoint. So I start with a vector, but now, as I said before, it's natural not only to have a viewpoint in the d-dimensional torus space, but to add one direction. So I had one direction, alpha 0. I take such a vector, and I just normalize it such that the sum of coordinates is equal to 1. Then I will consider the projection. So I have to think that I've added this direction. I've got my alpha direction. And then I will try to see what happens on the hyperplane orthogonal with the vector 1. Okay, that's an antidiagonal hyperplane. The coordinates of vectors sum up to 0. So I project along alpha on this hyperplane. And then I look at the unit hypercube. Well, that's just a representation of this unit hypercube. So why do I want to depict this? Is to show that we can see easily the rotation in terms of this unit hypercube. This unit hypercube tiles the hyperplane with normal vector 1. It's not difficult to see that. So it's an hexagon and it tiles periodically the hyperplane. So what I claim is that this map that I've depicted here, which is just an exchange of pieces, I've got 3 faces. So I consider my unit hypercube. I can take the lower, the upper one, project it. So I've got here some map, which is an exchange of pieces. You go by translation from this face here on the left to the face on the right, to the face on the bottom. It goes up. The largest one goes a little bit down. So you have an exchange of pieces, which plays the role of an exchange of intervals, which is also a classical object of dynamical systems. So you have this very simple map. What I claim is that this map is just nothing else than a translation of the torus. I've chosen some particular fundamental domain for your torus. So the torus is of dimension 2 here in this setting. So you can see the picture, the cube, you can see it from R3, but we come back to a 2-dimensional space. Okay, so this map is just a translation, a vision of the translation. The map which sends each face to its counterpart on the right, it's just congruent modulo the periodic lattice generated by these hexagons, by the vectors which generate these hexagons. So you have a lattice which is behind, and so this map is congruent to your translation that you started from. So we have added a kind of extra coordinate, as usual in arithmetics, and we have now a nice representation of rotation, translation. So why do we do that? It's just to revisit this result by Grebstadt-Lev, which says that if you take a parallelotope which is which has this nice property that the vertices belong to Z alpha plus ZD, you have a bounded reminder set. So what I claim that the counterpart, the illustration of this result is the following. In your fundamental domain, which was a projection of the unit cube, the 3 projected faces are bounded reminder sets. So it's just a consequence of Grebstadt-Lev. So what we have here is not only that we have bounded reminder sets for the torus, the 2-dimensional torus, viewed with respect to a particular fundamental domain. So we have bounded reminder sets, but even a partition by a bounded reminder sets. So it's already something interesting because, in fact, we are also interested in the global viewpoint. So we have a decomposition of the space into, large bounded reminder sets, but one can hope to get global view results in terms of these local ones. And also, if we come back to the ideas from discrepancy based on Ostrowski enumeration and based on the local behavior given by intervals expressed in terms of Ostrowski enumeration, that's how we get global results. So here we have these 3 sets, which are bounded reminder sets by direct application of Grebstadt and Lev results. So it's going from this statement to this geometrical view is immediate just by noticing that the translation, the projection involves the translation vector. Now the question is, can we do something better? Can we, what it means here to take, to look at some bounded reminder set and to look at what happens next. So I come back to the question I asked before. Now, what about these sets being in bounded reminder set and falling in a next bounded reminder set, knowing that have coded my orbits, I've ordered the action of the rotation with respect to the three sets. So looking at these new atoms, this refined partition under the action of the dynamics, give this picture with here 7 blocks. So to have an idea of where they come from, if I concentrate on this on the left, this triangle on the left, I don't know whether you see it with my mouse, yes. Then what happens here that you are on this face, this left part, and if you apply this map, you fall here on exactly on the right. And if you want to see where you came from, you have to come back to this lower face to see that the points here will come visit. So first this face on the left, and then the face on the bottom. So the 7 atoms of this refined partition tell you that you were originally in one of the atoms of the original partition, and then it tells you where you will be after the action of the dynamics. And then that would be interesting if all these sets would be again bounded reminder sets. We would have something which would work well in arithmetic terms, with the Kronecker partition, with the Kronecker sequence, the translation that is given by the parameter alpha, but also under the action of the dynamics. So that would be nice if they would be bounded reminder sets, but in fact, when you do that, you completely destroy this property of bounded reminder set. So you get a partition, but this partition does not behave well when you refine it with respect to the dynamics. So I don't just give a flavor of the proof. A necessary condition for being a bounded reminder set is that the areas, the measures of these sets have to be related with respect to the parameters of the translation. So they have to belong to this additive group generated by the parameters of the entries of alpha. So a naive proof is just to check that the areas of these sets do not belong to this additive group. For some parameters, you have to be to refine the properties, but that's why I say it's a proof. It's proof which works for almost all parameters. And also, all these objects that I present here belong in terms of dynamical systems to the study of pairing billiards in the hypercube. In fact, you can see these dynamics here, this translation as a billiard game in some hypercube, and there is literature on this. So we are a bit disappointed, in fact, when we look at these first examples of bounded reminder sets.
Sorry, Valérie, there is another question. Christopher, will you please unmute and ask away your question?
So I miss.
Is your question equivalent to asking that you have bounded? Christopher? No, we don't hear you. So is your question equivalent to asking that you have bounded reminder sets for both symbolic system R alpha and R alpha iterated 2 times square?
Exactly. And then I will ask even more. Now my aim is to have bounded reminder sets. So I would like to find bounded reminder sets which are bounded reminder sets for R alpha and pre-images, or as you said, it could be the twice R alpha, if I understand well your question. But also I would like now to find a partition of a fundamental domain into bounded reminder sets such that whatever the number of iterations you consider, you still get something which is a bounded reminder set. Which means that these sets, so I want to find a partition. I want to see only good sets in my fundamental domain. And I want to have the following property. When I am somewhere and I visit another atom of the partition and so on and so forth, I would like that all these quantities give you bounded reminder sets. So that's my aim, finding such multiscale partitions by bounded reminder sets. So I will revisit it in a few slides in symbolic terms, because it's maybe still a bit artificial, seen like that, just with this description. Where does this intersection come from? But the idea is to say that we want to be able to see, when you visit a set and you see the future, the other sets, we want this information to still correspond to a very good equidistribution property. So that's my aim. And now that's the outline of the questions I'm asking in this lecture. So how can we subdivide bounded reminder sets into smaller ones? Or to get such multi-scale bounded reminder sets? Can we do that with parallelotops? We have seen with the simple example of based on projections of hypercubes that it doesn't work that easily. Even on the second step, we don't get bounded reminder sets anymore. So my aim is to show you how to get such nice bounded reminder sets. I would like also to spend some time on this question of the local discrepancy, how small it can be. And also to show how to construct bounded reminder sets via symbolic codings of Thuswaldner translations in terms of continued fractions. But then we will see that the drawback, the price to pay to have something multi-scale for our approach, is that we won't have parallelotops anymore. So that's what I want to discuss today. The motivation which is behind is to come back to the one-dimensional case, where we consider one-dimensional translations, and when we have this simple dynamical system, which is plus alpha mod 1. Then, according to Kesten, if I divide the unit circle into two intervals of length 1 minus alpha or alpha, I've got a nice partition into bounded reminder sets. Each of those is a bounded reminder set. Now, from a symbolic viewpoint or dynamical viewpoint, it's quite natural to code the itineraries under the action of R alpha with respect to these two intervals. We will get infinite words, sequences with values in the alphabet 0, 1. These are called Sturmian words. So to be more precise, I've got a coding map. And then if under the action of my translation, starting from some point, so I iterate n times my translation, so I do in fact x plus n alpha mod 1. If I fall in one of these two intervals, associate to n a value, 0, 1. Okay, so it seems that I lose a lot of information. I start with alpha, and now I do some very simple coding of x plus n alpha. According to the information, I fall between 0, 1 minus alpha or 1 minus alpha 0, I put a 0, 1. But in fact, it turns out that we don't lose that much thing, that we have the two systems are isomorphic. That is to say, the translation on the torus and the shift map on this set of sequences. So the shift map is just the map which associates to an infinite word, to a sequence. The shift of this sequence, you just make this simple operation. You just rename, you just shift the indices of this sequence. So that's, again, a dynamical system. So you have a dynamical system, that is to say, just a continuous map in some compact domain here, translation. And then in a symbolic view world for infinite sequences, we have a map, a shift, classical map in symbolic dynamics. Symbolic dynamics is a study of dynamical systems made of sequences, words with values in some here finite alphabet. So we have a commutative diagram, we have an isomorphism. It cannot be a homeomorphism between both systems because the topology is not the same. Here we have a contour topology, here we have something Euclidean in some sense. So we can't have homeomorphism, but okay, up to some countably many points where the bijection fails, we have this nice diagram, so which conveys the idea that we haven't lost too much information going from Kronecker sequences to the symbolic worlds. So that's the theory of Sturman worlds, which started all the theory of symbolic dynamics from Morse Lund in the 40s, and then it's completely related to continued fractions, and we have nice properties. And if we look at the question of whether when we refine the partition, you get again bounded reminder set, everything works well through Keston. So you can refine the partition, and that gives you multi-scale bounded reminder sets. So that is a kind of guideline for us to continue to develop this theory in higher dimension, continued fractions, and so on and so forth. So I will give you another example on 3 letters now. And this example comes from the 80s and works like that. You start with a substitution, that is to say, a rule which produces sequences, infinite words. Very simple rule, you replace letters by words, like here. You replace 1 by 1, 2, and then you continue. You replace 1 by 1, 2, 2 by 1, 3, 3 by 1, and so on and so forth, and you create an infinite world. So instead of starting from alpha and getting a coding, my point will be to start from a potential coding, associate with it an alpha, a translation. So I start with an infinite world, and I claim that I will produce with it a translation and bounded reminder set starting from a coding. So I start with this. With such a rule, I can associate a matrix which makes this rule commutative. I just put in the matrix in columns the data that the image of letter 1 is the first column. It contains a 1, a 2. The image of letter 2 contains a 1 and a 3. The image of the letter 3 contains a 1. Okay, so that's a matrix. You look at its characteristic polynomial, which is irreducible. It's the minimal polynomial of a Pisot number. That is to say that you have one eigenvalue, one root which is larger than 1. The other ones are smaller than 1 in modulus. So in terms of applications of iterates of this map, so what we can see in terms of matricial terms, it's that you have an expanding eigendirection and a contracting eigenplace when you iterate this matrix. And iterating this matrix is a way to understand what happens when you iterate such a map. So to understand how the letters 1, 2, 3 behave when you iterate something like that.
Sorry, Valerie, there is another question from Christopher. Christopher, will you try to unmute again, or?
Yes, is it working? Okay, so did you just say that the parameters alpha for which you have arbitrarily defined partitions into bounded remainder sets are precisely those for which the system will be self-similar? Or self-induced, if that's the term?
We will find nice bounded reminder sets. But my point will be to say that we can go beyond self-similarity. So I start with something similar, and we will see that we can go much further than that.
Okay, so and you will be finding arbitrarily defined partitions for these new ones.
That is to say here, with this example, we are just considering cubic entries and the self-similarity, the algebraic self-similarity, which is beyond this process, leads to cubic entries. But my point will be at the end of this lecture to provide you some theorem telling you that we can do that for almost every parameter.
Okay, thanks.
Thank you for your question. So I continue with this example of cubic example, and then my point now will be to start from an infinite world like here, and then to create a direction. So the fact that we have a Pisot situation implies that, in fact, if you replace in an infinite world letters by vectors, so you get a broken line in Z3, so you read 1, 2, 1, 3, you get a broken line. What I claim is that this Pisot property that we had, one eigenvalue larger than 1, the other one being smaller than 1, makes that this infinite world stay within bounded distance of this line, which corresponds to the eigenvector associated to the dominant eigenvalue of the matrix. The cubic number root of beta to the third equals beta to the 2 plus beta plus 1. So you create an infinite world, and when you project, you can get bounded. So first, you get points which stay bounded distance. So you get some compact set, and what is super important is that this compact set is in fact a fundamental domain for the torus, and you can even divide this compact set into 3 pieces, which will give you a bounded remainder sets. So that's what I want to illustrate in the next slides. So we start with this strange self-similar rule, substitution. You create an infinite world, and I claim that this infinite world will create some fundamental domain for the torus, which depends on the combinatorics on this choice of this rule that we have taken, but which will behave very well. So the drawback is that we have a weird fundamental domain because we have a set with fractal boundary. The good news is that it provides a partition into bounded remainder sets, which will be multi-scale. So maybe the best is to illustrate this with an example. So I still take the same substitution. This is still self-similar rule. This is a cubic parameter given by this matrix. We have this rule. So if you want to catch a parameter, you can take such a matrix and then associate it with a rule. If you give me some matrix which is Pisot, which Pisot in the sense that it's its characteristic polynomial is the minimal polynomial of a Pisot number, then all this works well. So we can make such a rule, create an infinite world. And then since I want to understand what happens, in fact, transversely with respect to the direction that I am approximating, which is an eigenvector of the matrix, it's nice to lose one dimension and to arrive to the contracting plane of the matrix. So what happens here when you iterate this? In fact, you create something which goes in the expanding direction of the matrix. And then we want to understand the dynamics on the contracting plane of the matrix. So we kill the expanding dimension and we look at what happens transversely. So if we keep in mind what we do, for instance, for continued fractions, it's often the case that we represent continued fractions like approximations of lines by points in the plane, in Z square, and not by looking at points Pn, Qn, with the Pn, Qn being the convergence for continued fractions. So it's classical to look at continued fractions not on the unit interval only, but in R2 and Z2. So that's exactly what we do. We have one extra dimension. If our target is T square, we have one extra letter, one extra dimension, but we kill it in some sense. So we have a 3x3 matrix, but we want to understand something which is of dimension 2. We have added this extra dimension to understand what happens in the plane. So I will replace letters by canonical vectors, and then project according to this projection, which makes me understand what happens in the contracting plane of the matrix. So what happens here? I start with the 1, I replace 1 with the red dot. Then I see a 2, I put the vector P of E2 after my point red, and so on and so forth. I get again a 1, a 3, red, and so on and so forth. So I just I'm just projecting this word with this rule that I replace vectors by letters by vectors. And then what I get, so I get countably many points. Let's take the closure to have something with which we can work. And we get this so-called rosy fractal. So property, which is quite a priori surprising, is that we get a periodic tiling of the plane by this shape, which means, in other words, that this is a fundamental domain for the two-dimensional torus. And also, the choice of the colors has been given by the letter we saw. There was no reason for these colors not to interpenetrate. They create different areas, separated areas, and each of these areas is a bounded reminder set. And to prove that this set is compact and each of the area is a bounded reminder set, it's just a question of linear algebra. It's just because of this property, Pisot property, one eigenvalue larger than one, the other one smaller than one. So nothing very deep here. The deep thing is that these three domains do not intersect, except on sets of zero measure, that we have a fundamental domain. No, that's more difficult to prove, but that's not too difficult neither. But here we need some more analysis to prove this kind of results. But knowing that we have a bounded set is just linear algebra. So that's what Rosy did in the 80s. He proved that, in fact, this system, this infinite worlds, the dynamical system generated through this infinite world generated by this substitution. So the dynamical system is the shift acting on this set of codings. So this set of codings behave well. It's isomorphic up to a set of zero measure that's hidden in the measure theoretically notion of isomorphism. But this symbolic representation is isomorphic to our translation on the two-dimensional torus given by this cubic parameter. So if we come back to what we have seen with the example of the projection of the cube, okay, it's a more sophisticated fundamental domain of the torus, but that's a fundamental domain and a partition into bounded reminder sets, and they have the nice property of being multiscale. So we have an example which is not parallelotopic, which is similar, which dates back from the 80s, saying that, okay, we can make what we wanted to do, multiscale bounded reminder sets. So now this leads us to the question of Christopher, is it, do we need some self-similarity here? So my point will be to say, we can go behind this through the use of continued fractions. So that will be my next move. And to recap what we have seen, in the same way as we can have a representation with this fundamental domain of a translation as this simple exchange of pieces, here the translation is just something now that can be seen again on this fundamental domain. And this is exactly the same stuff. We have a translation on each of the atoms, but now we have some weird boundary. So just to recap, if we want to produce bounded reminder sets, now we have a strategy, which is to find word sequences that stays within some vector that directs, this is the alpha. And then we project these infinite worlds. And then if we are lucky, we find fundamental domains. So that's the overall strategy. So now I enter some symbolic world, and I have to give some symbolic definitions that I use implicitly in the previous slides, but I want now to spend time giving them more specifically. So since we've seen with the previous example that it's interesting to start with sequences to get information on translation, I give these definitions, which are quite natural. Given a sequence in the finite alphabet, I can consider the frequencies of occurrences of letters. So I want to see how often I find in the first letters some given letter and if the limit exists divided by n, that's the frequency. So if we take, if we have in mind Kronecker sequences, that's the same as saying, okay, a sequence falls into some interval. So falling into some interval here is just to say, okay, you find one letter. And then the discrepancy is, okay, you want to compare the number of times you see one letter minus its expected value as before for the discrepancy. So as for the discrepancy, we'll take some supremum over something. So we take a supremum over the prefixes, maximum over the letters. So that's a notion of symbolic discrepancy. But if we, so this is inspired by the discrepancy for Kronecker sequences. But in the case of Kronecker sequences, we take the supremum on all boxes. Here, it's a bit disappointing. We take only letters. So that would make sense to have the same definition, not counting how often you find a given letter, but how often you find a configuration of letters that you find in your word. If you find a configuration AB, if you find a letter AB, well, let's say my letters are 1, 2, D. So if you find the pattern 2, 3, for instance, how often do you find it? And then to understand that, that's exactly where this notion of having an atom intersecting with its preimage, that's exactly what it means. You want to see that you were in some atom of the partition labeled by 2. After that, you saw a 3, you were in the atom 3. So that means to say that you are in the atom 2 intersected minus R alpha minus 1 atom 3. So that's the connection with the previous viewpoint where we wanted to refine partitions. So from a symbolic viewpoint, it's quite natural. You want not only to see whether your letters behave well, are well distributed, you want to see also whether any kind of finite pattern that you see in your sequence behaves well. If you make a parallelism with normality, when you consider normal number, you don't ask only whether your letters occur with same frequency. You want every pattern, every word to occur with the same frequency in a normal number. So here we consider letters, but not only letters, every kind of pattern. So this is why we want to multiscale this multiscale notion. And then I just want to make a small parenthesis for nice results concerning this notion from dating back to Niederreiter and Tiedemann. And they ask the following question: how small can this quantity be? So now I'm given some sequence, some frequency vector. I assume that the sequence is sufficiently well organized so that the frequencies exist, the limits exist. I've got this notion of frequency, of discrepancy, sorry. I'm still just on letters for the moment. And then first result which occurred were given by Niederreiter, which was able to construct sequences for which the discrepancy was smaller than D-1. Then he expected that you would reach alpha for every alpha by, that is to say, that if you take all the alphas, you are always able to find some sequence for which the discrepancy is smaller than 1. By the way, the fact that the discrepancy is bounded means that alpha corresponds to the frequency of occurrences of the letters. If you have a bounded discrepancy, you divide by n, you come back to the frequency. So that means that the alpha is the frequency of occurrences of letters. So Niederreiter was able to prove that we could find words of discrepancy smaller than 1. Tiedemann was able to refine it with this. Meyer also proved that this quantity here is related in terms of D. That is to say, whatever alpha, you can always find an infinite word for which the discrepancy is in 1 minus 1 over 2D minus 2, where D is the number of the alphabet on which your infinite sequence, your sequence lives. And then Tiedemann provided an algorithm generating such sequences. And then we also know that if you consider minimal translation, that is to say linearly independent entries, then you're larger than 1 minus 1 over D. So that's the situation. So we had this nice construction of Tiedemann. we have the situation of Fibonacci, where you have a dynamical system, a translation. We have the situation of Sturmian worlds, you have a translation. So now a natural question is to ask, for this construction by Tiedemann, which have a priori nothing to do with the translation, there is nothing Kroneckerian beyond, it's just a construction. It says, okay, I can find very nice, I can find sequences with values in a finite alphabet with a nice repartition of entries so that we have a very small discrepancy. And then the question that we have asked with my colleagues was whether this construction of Tiedemann would be related to Kronecker sequences. So finding sequences which make a discrepancy smaller than this bound, knowing that this is the best bound possible if you take all possible alpha. That is to say, if you take any epsilon and you reduce this bound, you can find a parameter alpha and a sequence for which the discrepancy is larger than this quantity minus epsilon. So the result we've had with Olivier Carton, Nicolas Chevalier, Wolfgang Steiner, and Henri Yassaoui is that, in fact, this construction by Tiedemann, which was a really combinatorial, involves a translation. That is to say, we are making a symbolic coding of a translation. That is to say, we find again a fundamental domain. We find again atoms of this fundamental domain in terms of polytopes. So these are finite unions of polytopes. And the translation is behaves like nicely again. It's a translation by a factor on each of the polytopes. So these atoms are bounded reminder sets. This just is a rephrasing of the fact that the discrepancy is bounded. So we have this surprising situation in some sense that starting from a different viewpoint, a combinatorial viewpoint, I want to find words that have a bounded small discrepancy. We find again a translation which is behind. And just to make the connection with what we saw before, instead of having this exchange of pieces that we've seen with hexagons and projections of unit cubes, we find such weird, these are still polytopes, but weird shapes in the sense that they are maybe not connected, they are not convex. Well, we have small, strange atoms of these partitions. Okay, so that was just a connection with different view questions on bounded reminder sets taken from a symbolic viewpoint. I would say that the classical arithmetic viewpoint is to say one box, to take one set, one box. The dynamical and symbolic view one is to say, I don't just want to have nice sets, I want to have partitions that behave well with respect to the dynamics that give you bounded symbolic discrepancy for letters and factors. I know I see that the time is flying, so to answer also Christopher's questions, which is, can we do such things? Can we have multi-scale bounded reminder sets? Okay, we can extend the rosy construction we've seen. We take a multidimensional continued fraction, which produces matrices. So it's a way of looking at continued fractions. It's to say that you produce non-negative matrices, and then you approximate some parameter by action of these matrices acting on the positive octant, well, on R plus D. That's the view of continued fractions. Usual continued fractions, you can see your parameter as being generated by products of 2 by 2 matrices, and these matrices in the classical setting generate the Pn, Pn-1, Qn, Qn-1. So it's classical. It's always the same idea as I said. You add an extra dimension to go from something on 0, 1 to something linear. So continued fractions do the job. They produce matrices. We have matrices. We can take substitutions. We can take words. And now we have all the machinery that allows us to, from words, to be able to construct fundamental domains. And this is something from a dynamical viewpoint, which is classical in terms, here we have ideas from renormalization, but I will not spend too much time on this. Now, our result is the following, is that you take any exponentially convergent multidimensional continuous fraction algorithm, which satisfy this Pisot type condition expressed in terms of Lyapounov exponent. So that means that your algorithm is strongly convergent. So Lyapounov exponents correspond to the logarithm of the eigenvalues, singular eigenvalues. And so this is why my one eigenvalue larger than 1 becomes a 0. I took a log. So suppose you have a continuous fraction algorithm having these classical properties on Lyapounov exponent. Then we can develop our machinery for almost every parameter. We can understand the translation onto us in the sense that we can provide a fundamental domain and multi-scale bounded reminder sets for this translation. So all what we've seen with the Fibonacci case can be extended to this case of continuous fractions. So that is quite nice. Just the point that we have something for almost every parameter, but that's quite natural, in fact, because we have a measure of viewpoint. Lyapounov exponents are defined almost everywhere. So it's not that surprising that we can do that for almost every parameter only. Well, it has been applied in different settings. So the need of having symbolic codings is not just for people from symbolic dynamics. It can be used in the context of Schrödinger operators. So everything works well for us. But I would like to finish with you. Just here, I just show you an example of a continuous fraction algorithm. So I don't know whether you, yeah. So outside it was noisy, but I hope we haven't heard the noise. It's perfect. So it's an example of Jacobi-Perron algorithm, which creates matrices of this shape, just to give you an image of this. But my last slide will be the following. We are happy. We are able to make multifractal bounded reminder sets. But I guess just this assumption that we need strongly convergent algorithms. So we need the second Lyapounov to be negative. We want the second eigenvalue, which to be smaller than 1, that the Pisot type condition. And that is known from work of Lagarias, for instance, that multidimensional continuous fractions create you approximation, Dirichlet type approximation governed by 1 minus lambda 2 over lambda 1. And in fact, we have realized with numerical experiments that in dimension 10, which is not huge, in fact, the classical algorithms, all the classical algorithms we took provide a second Lyapounov exponent, which is strictly positive. So I will just end with this, saying that on the one hand, we are very happy. We are able to produce bounded reminder sets with continuous fractions. So we thought that most of the work was done. And then with these numerical experiments, we realized that classical continuous fractions maybe do not behave as was expected from their behavior in dimension 2. We have a problem, maybe a problem of strong convergence in dimensions around 10. And so now our point now is to confirm or not these experiments. And I will just also finish with, just a conjecture, asking whether the price to pay to have this concept of bounded reminder sets and partition is that we can't have smooth boundaries. And I will stop here.